Cool. All right. Yeah. So welcome everybody. My name is Ezra. I'm covering for Hannes today, and today we have the pleasure of hearing from Akhil Premkumar. And Akhil, is that how you pronounce it, or let me know if
Yeah,
it's
that's fine. Yeah.
okay. Let me know. Who will be discussing his paper, Neural Entropy. So with that, I'll hand it over to Akhil to get started.
Let me try sharing my screen. Can you see my screen?
Yep.
Okay, good. Okay. Well, Ezra, thanks for having me here, and thanks to
Yeah.
Hannes. Um, Unfortunate that he couldn't be here. I should also thank Morris for nudging Hannes to have me on. So
Oh.
this this talk is actually uh, my attempt at understanding aspects of machine learning from an information theoretic point of view. So I'm not an expert on machine learning. I'm a theoretical cosmologist by training, but last year I just randomly got interested in machine learning because it had some connections to some of the work I did during my PhD. And so um, basically, I'm trying to understand essentially diffusion models through a combination of two classic thought experiments in physics called Maxwell's demon and Schrödinger's hotcast experiment. So all of the work you'll see here, this talk is basically a quick summary of basically the content of these three papers, but mainly the paper in the middle, which is the neural entropy paper that Ezra mentioned at the beginning. Um, although only my name appears in these papers, I should actually acknowledge a few people before I start. So they are first Austin Joyce, who is a physicist at the Kavli Institute, and he hired me at Kavli to work on theoretical cosmologist and had the good grace of not firing me when I started doing all this machine learning stuff. So I'm grateful to him. The second is Lorenzo Orecchia, who is a professor in theoretical computer science here at the University of Chicago. I've had various great discussions with Lorenzo, specifically about kind of seeing most of these ideas from a computer science perspective. And finally, I would also like to thank Billy Cottrell, who used to be a string theorist, but now works at Jump Trading for many valuable discussions and very detailed feedback over the last year. All right. So let me just get right into it. I'm going to start with a very elementary problem, which is the following. Suppose there was some probability distribution PDX shown in green here, and we only had access to this distribution through some of its samples. So we don't know what the distribution is. We just are given a bunch of samples from this distribution. The question is, what can we say about PDX from looking at these samples? Well, in particular, can we actually just reconstruct the distribution? So this doesn't seem like an unreasonable thing to ask because after all, if you just stare at the distribution or stare at these samples, you can see that there is a larger concentration of these samples at some points or some regions, and there is a sparsity of points in other regions. So that should give us some idea about what the underlying distribution is. The problem is that there are, in fact, many distributions that could have generated the same set of samples. And this is especially true if the number of samples is very few, right? So I've represented a couple of different options here, but there is, in fact, a continuum of possibilities for the distributions that could have created these red samples. And all of those possibilities have different probabilities of being the true answer. In fact, that means there is a distribution of distributions, as I show here, right? So this distribution of distributions is basically what, or the statement that the um, uh, finiteness of the number of samples basically kind of makes it difficult to disambiguate the true underlying distribution is just the statement that the width of this distribution of distributions is basically 1 over root n, or controlled by 1 over root n. We hope that the true underlying distribution is close towards is close to the peak of this distribution of distribution. So if we have enough number of samples, we'll be able to kind of get a good approximation of PD. So I'm going to draw this in a slightly different way because I want to kind of make a connection to physics. So I'll represent the same figure in the following way. So I'll draw my candidate distributions in on the left here as these curves here, and then my distribution of distributions I'll kind of represent like this. So what I want to show you here is what happens to these curves as I have more and more samples to play with, right? So I'm going to put more and more samples on along this line here, and I want you to pay attention to how the shape of these curves evolve as I do so. Oh, did someone have a question? Someone I think drew on the screen.
Oh, yeah, it looks like somebody drew on screen. Just in general, let's try and don't draw on the screen. Raise your hand. Yeah, no worries.
Okay, I think
If you have
there's
a
a question.
question, you can just do the little raise hand emoji or something like that.
Okay, so I saw something on the chat. I'm trying to access the chat. Give me a second
Oh
here.
yeah, I think the person who drew that was just apologizing.
Oh, okay.
Yeah.
All right. All right. So when I put more samples, this is what happens. Observe how these candidate curves change and how the distribution of distributions change. So these yellow and magenta distributions are basically, other candidates that could probably be the answer, as indicated here. And you see that the viable candidates basically start converging to resemble the same, or start converging to have the same shape as the true underlying distribution, right? And the distribution of distribution becomes sharply peaked around the true distribution PD. And this situation should actually remind you of what happens in statistical mechanics, where if you take something like, a container of gas, then basically you write down the partition function for that object and you compute probabilities with that partition function. And the probability distribution or the energy, for example, will have this form where Fe is the free energy, which is a convex function that has a particular unique minima. And if you
What
actually
is
work
E
it
here?
out, what's that?
What is E? Is E like some
Energy,
region
it's
of?
just energy. So I'm just looking at the canonical ensemble here.
Oh, I see. So what is F? What is F of E in this case?
F is the free energy, so it's E minus ds.
Oh, okay. All right. I see.
Yeah, it's just some convex function. So the basic point I want to illustrate is that F is an extensive quantity, so it depends on the number of particles. And so if you work it out, this expression actually has this form, e to the power minus n times some convex object. And that's why the distribution actually becomes sharp in case of statistical mechanics. You have basically a bunch of microstates, but the most probable microstates are always going to kind of pile up around under this maxima. And all of those microstates will basically give you the same answer for the macroscopic measurements you make of the system. So that's kind of the connection that I'm trying to make here. So the microstates in a statistical ensemble are analogous to these candidate curves here. So that's all I'm saying. And so the question is, can we then make an analogous statement about the learning problem, which is, can we say that given a large number of samples, that the distribution of distributions also has this asymptotic form? And in fact, in many cases, you can show that it does have that form. And taking a step back, I also want to point out that in a very, very oversimplified sense, this is what all generative models are doing. They're basically taking some training data and trying to approximate the underlying distribution, right? And so that when you sample this distribution, you get new samples which have essentially the same properties as the training data. Okay.
Wait, so
Now,
just oh,
yeah,
sorry. Keep going.
please ask questions.
I was just gonna
Yeah, please
ask. So
feel
I
free
just
to
want to make
interrupt
sure
and ask
that
questions.
okay, awesome. So I just want to make sure I'm on the same page with you about like this kind of
Uh,
stat mech interpretation of what's going on here. So you're describing
uh,
some ensemble whose microstates are the possible distributions from which these samples could have could have come, and then you're saying that you're basically trying to say that we have some Boltzmann distribution over these things, and then you're trying to connect the number of samples, and is the number of samples here to this
Yes.
beta is usually inverse temperature, if I understand correctly.
Beta is inverse
Or, oh,
temperature, yes.
oh, so we're kind of saying that the functional forms look the same, and so this is you
Yeah.
can kind of interpret it as a um, you can so wait, the probability of E. So E is you said E was an energy rather than a
Yeah.
microstate.
So E, in that case, E is a number. So you can think of E as basically, a label on the microstates if you want to think of it like that. But E labels actually many microstates. But I'm drawing like a rough analogy here. So this object, this is a function of like a scalar, right? This is a function of this is a functional of functions. So
Oh,
this
sure,
is,
sure, sure. Okay.
yeah. So
I see,
so
I see. So the
or
thing we
like,
actually are looking at is the bottom, is this Boltzmann
yeah,
distribution over this curve of candidate
right,
densities. Gotcha.
exactly.
Okay.
Yeah.
All right, I'm with you.
Yeah. So, yeah, so, this is kind of a clue as to, this connection between StatMech and basically the setup of generative models, right? And as I said, all generative models are in principle and in a very oversimplified sense trying to do exactly this problem. But the reason I decided to focus on diffusion models is because in diffusion models, this form actually becomes very explicit in a straightforward way. And that's because diffusion models were kind of designed or they were invented with ideas from non-equilibrium statistical mechanics. So it's kind of baked in. So the structure kind of reveals itself very quickly. Now,
And just
so
yeah,
go ahead.
I was gonna ask, like, is so this question mark, is this are we claiming that this is true, or are we like, is this wishful thinking that we would hope some result like this is true, or
Yeah, I'm basically saying I'm not I want to put the question mark there because I don't want to claim that this is true everywhere in all generative models. I don't
I
know
see.
yet. I'm just saying, it kind of has a resemblance. The problem that I set up here has a resemblance to the StatMech problem, and therefore I wonder if this is true. And in fact, in many cases, it is true. So I'm giving myself a little bit of wiggle room here. That's all.
Gotcha. Okay. All right. Awesome.
Yeah. Yeah. All right. So diffusion models, there are literally thousands of papers written on diffusion models. But when I started, reading about this stuff, the paper that I found most insightful is this paper from almost a century ago by Erwin Schrödinger. Um, so this was a seminal paper that basically I guess, opened up the field of optimal transport along with other authors, but this was one of the key papers. And at the heart of this paper, which by the way, I encourage all of you to read because it's really a beautiful paper. It's only like 10 pages long and it's very elementary, but the arguments are amazing. So at the heart of this paper is the following thought experiment. So Schrödinger asks you to consider a diffusive system. For example, like a drop of ink in a container of water, for instance. And let's kind of look at what happens to the system if you just leave it for some time, which is that, Brownian motion kicks in and it kind of distributes the ink particles, and the ink particles basically homogenize and get distributed as some stationary distribution after we wait for a sufficiently long period of time, right? So the question Schrodinger asks is the following. If I now take this container and I just leave it uninterrupted for a while, what is the probability that these ink particles will be reconfigured back into its original state? Okay. Or in other words, what is the probability of reversal? Now, this might seem a little bit like a strange question because we never see things undissolve themselves in real life. But this is Brownian motion, and in the space of possible outcomes of Brownian motion, there are distinct possibilities where you do recover the original state. It's just that the probability of those events happening is super suppressed. It's exponentially suppressed, which is why we never see it happening. but that doesn't mean that the probability is zero. So Schrödinger is basically asking what that probability is. In fact, there are many ways that the particles could reconfigure themselves. So let's take a look at a couple of ways. So first, let's imagine a scenario where all of the particles get some kind of spontaneous kick. So they kind of reverse themselves and bring themselves back to the original state in a very short period of time. So it's like a spontaneous recovery, right? And another scenario you can imagine is that the particles start in the equilibrium state and they get many number of small kicks, which together conspire to bring the particles back to its original state. So both of these are different ways of arriving back at the original situation. And in fact, there is a spectrum of possibilities between these two, right? These are not the only two possibilities, but let's just kind of focus on these two kind of extreme limits for the time being. And we can kind of distill Schrodinger's question into the following slightly simpler binary problem, which is out of these two possibilities, which one is more likely? So both of these are extremely rare events, but out of these two, which one is more likely? Now, this is kind of the key idea that runs through the rest of the talk. So I'm going to take a strategic pause here so we can think about this for maybe like, I don't know, 20 seconds. So I want you to kind of think of an answer in your head and maybe like keep it close to yourself.
So in A, the transition is from this like nearly diffuse state, like on the left, like immediately back to the start.
Yeah, yeah. And in the second case also, it's from the same initial state, but it's kind of through many, many small transitions.
Right.
Okay, so let's try and solve this. There are many ways to solve this problem, but I'll just discuss one solution, which I think is particularly pedagogic. Um, so let's consider an even simpler problem, which is the problem of a Gaussian random walker. So I'll consider a one-dimensional Gaussian random walker that moves along X. And I'm going to show the time evolution, or I'm going to show you a couple of trajectories of that one-dimensional Gaussian random walker. So this random walker is assumed to have mean zero, which means it kind of just wants to hover around zero most of the time. But the first scenario is where this walker actually does an abrupt jump, which is analogous to kind of the rapid reversal you saw earlier. And in the second scenario, the walker kind of moves in one particular direction in a very persistent way. So this is kind of analogous to the gradual reversal you saw earlier. So both of these are rare fluctuations. So these are rare events because usually the random walker would kind of, like I said, hover around this gray line at zero. But instead, what we have here is that the walker, no, I'm sorry, yeah, sorry. You can still see my screen, right? I click something. Can you
Yeah.
still see my
Yep.
screen? Yeah, okay. I'm
Yep.
sorry. I see I clicked something off screen. But anyway,
Oh yeah, you're
uh,
good.
yeah. So the both of these are extremely unlikely events, but one of these is actually more likely than the other. And to figure out which one that is, let's denote the size of the transition, like the distance covered by L. And in the first case, basically the walker covers most of this distance in a small time step delta t, right? And this is a Gaussian random walker. Therefore, the probability of the first event basically is dominated by this particular transition. And therefore, the probability of this one large jump is e to the power minus L squared over delta t, again, because it's a Gaussian random walker, right? In the second case, the random walker basically makes many small jumps, each of which has a much smaller size, but there are many of them kind of strung together. And if you actually work it out, it turns out that the probability of that transition depends on the total time it took and that probability is e to the power minus L squared over uppercase T. And since uppercase T is a much larger number than delta T, the power of the exponent is closer to 0 there, and therefore we conclude that the gradual trajectory is actually more likely. And that is to say that in the kind of the problem, reversal problem we considered earlier, the gradual transition is much more likely than the spontaneous reversal. Okay. In fact, Schrödinger goes beyond this, and he shows that the most probable reversal is not just any gradual transition, it's a transition that basically looks like a playback of the forward process. So this is, I actually want to show you some of Schrödinger's mathematical results. So I'm going to introduce a few mathematical symbols here. So I'll denote the equilibrium distribution on the left here as P equilibrium and the ink drop by PD. Let me denote the forward process as just a simple Brownian motion with the strength of the noise being sigma. And if F is the forward transition probability corresponding to this process, then applying F on P equilibrium basically gives you P equilibrium back, because P equilibrium is just the stationary point of the forward process, right? So it doesn't do anything to that process. Similarly, I can use another stochastic differential equation to describe the reverse process. And basically, if I have the reverse transition kernel for that, then applying that reverse transition kernel to P equilibrium brings me back to PD, right? So Schrödinger's result is simply the following. The probability that you get PD given P equilibrium basically is the exponent of the negative of n times the KL divergence between R and F, where the actual expression for that KL divergence is written below. I will give you a more intuitive explanation for what the scale is in a few slides. But for now, you can think of it as basically some sort of KL divergence between the path measures for the reverse and forward processes. Okay, and when you stare at this, it's kind of clear that this form has exactly the same structure that I pointed out to you before, right? The connection to statistical mechanics and the learning problem in that slide. So you kind of see where the parallel already becomes revealed here when you look at the Schrödinger argument. Go ahead.
Alec is asking, what is R? I think R is just the reverse transition kernel on the right.
Yeah, exactly. R is just the reverse so it is the transition kernel corresponding to this reverse process here. So it is the kernel that when you apply to P equilibrium brings you back to PD. Does that answer your question? Okay. So let me try to unchat.
And then someone is also asking about F, and I guess
Okay.
F is just on the left.
F is similarly, F is the transition probability for the basically the underlying dynamics of the system. So it's a transition probability corresponding to this diffusive process. Yeah. Why did I use the KL divergence? Well, I did not use the KL divergence. This is actually a result from Schrödinger's paper. In fact, so I've given this talk to a bunch of people, and whenever I give it to physicists, I get asked the same question, which is the KL divergence actually was introduced in a paper around 1950 by Kullback and Leibler. But the paper that I'm discussing now is from 1931. So how could Schrödinger have known about the Kullback-Leibler divergence? And the answer is that Schrödinger just anticipated the KL divergence by 20 years. So the expression for the KL divergence is in Schrödinger's paper from 20 years before the Kullback and Leibler paper. But there is an actual derivation for why the KL divergence in particular appears here. It comes from taking Stirling's approximation of a certain combinatoric expression, just like you usually do in statistical mechanics. And I would, again, strongly encourage you to look at Schrödinger's paper. There is a very
So is this the paper where I actually don't know. Did is one of Schrodinger's papers the one where he defines like I mean, nowadays people talk about Schrödinger bridges, and it's not clear to me if this was something that was like posthumously attributed to him, or if like it seems like basically that's kind of the BR that you're trying to learn
Yeah,
here
yeah.
is
The core idea of Schrodinger's bridge, which I will actually show in a few slides,
okay,
is
great.
it's basically this thing. Yeah. Yeah. But Schrodinger's, I mean, and to be more precise, Schrodinger's bridge is the probability distribution that interpolates from this to this. But I'll show you. Just wait for it. Thanks for the questions, though. Okay. All right. So I want to also illustrate this result in a diagrammatic way. And what I'm going to do here is I'm going to plot a function of the same form as the right-hand side, but I'm going to replace the kernel R with a generic transition probability T. So T here is a process that starts at P equilibrium and takes you anywhere, whereas R was a process that started at P equilibrium and brought you back to PD. So T basically starts at P equilibrium and it can go to PD, it can go to anything. And you know that the KL divergence is a convex function which has a minima when the arguments are equal. So on the T plane, if you identify the point F, then that's the point at which this function has a peak, because the exponent here is the negative of a convex function. Now what I'm going to do is on this plane, I will identify the locus of all points that basically take you back to PD, right? So that basically accomplished the reversal. And here's what that looks like. So this black line represents all of the ways in which you can start from P equilibrium and go back to PD, right? And the orange line corresponds to the probability of each of those events happening, okay? R is the process that looks exactly like a playback of the forward process. And that is the point which corresponds to the peak of this orange curve, right? So for example, the rapid reversal process you saw earlier could be a point somewhere on the tail here, right? And that's why it's much more unlikely compared to the playback reverse process. Now, this is a very exaggerated diagram. If you have a large number of particles in the system, this peak is going to be an extremely sharp peak at F, which means that this orange curve will be almost a flat line, lying flat on the dashed black line, and with maybe like a tiny hump at R. So therefore, by the usual rules of asymptotic analysis, that's how we basically uh, say that the probability of getting PD back from P equilibrium is dominated by the peak of this orange curve, which is at R. In other words, this probability is just the value at the star here, right? And you can also think of the KL divergence in this picture as just the gap between F and R. So that little purple line there, that is the KL divergence that appears in the exponent in Schrödinger's result. Okay. I also want to point out one more crucial thing, which is the following. Suppose I replace my forward process with a slightly more benign, more gentle process. So what I mean by that is I actually reduce the strength of my noise here, right? Which means the corresponding reverse process, which has to look exactly like a playback of the forward process, also has to change, right? And doing so also changes the arguments of the KL divergence here. Now, if I make the forward process slower, the corresponding playback also becomes slower. And now we have this intuition that if you take a slower process, the probability of that process is actually greater than that for a more rapid process. And therefore, making the reverse process slower means that this peak should actually travel up the curve, right? And in fact, that's exactly what happens. So if you make the forward process slower, F and R kind of come closer together, which means that this gap actually becomes smaller, right? It should also be clear to you just from staring at all this, that what I'm really talking about here is just the second law of thermodynamics. And this scale divergence here is just the total entropy generated in the diffusive process. Okay, so let me explain that a little bit more. And to do that, I'll switch to a slightly different visual motif because I want to represent time evolution. So what I'm going to do here is, the dash black line was basically all of the transition probabilities which uh, takes you back to PD. So the entire T plane would take you back to, or would take you from P equilibrium to any process, but the points on the dash black line exclusively take you back to PD. Does that answer your question? Okay, great. All right, so in this new diagram, what I'm going to do is I'm going to represent the equilibrium distribution with the simple Gaussian shape here, and I'm going to represent my quote-unquote ink or data distribution with this slightly non-trivial looking distribution on the right here. I'm going to denote my forward process by blue for the rest of the talk. And I'm also going to introduce a confining drift term so that my equilibrium distribution also is, some sort of a confined thing. Basically, I'm removing the boundaries from my beaker and I'm replacing it with this confining drift term. All right. So if I apply the forward process, which is just a diffusive process, to my PD, it slowly converts PD into P equilibrium. And as it does so, it's basically erasing information from the system. So PD had some sort of nice pristine structure, but then it kind of becomes homogenized into this P equilibrium, right? It all of its nice structure gets erased. And so S dot is a measure of how much information is lost during the forward process. Okay. And that's a way to think about, or that's usually how we think about non-equilibrium processes. We think about it in basically this direction. But using Schrödinger's result, we can also think about it in the other direction. So here's what I'm going to show. I'm going to apply the forward process again on P equilibrium. And remember, if I apply the forward process on P equilibrium, nothing happens because P equilibrium is already the stationary state of the forward process. But I'm also going to apply the reverse process. If I apply the reverse process, I will get my PD back. And what I'm going to show here is basically the evolution of P equilibrium under the influence of both of these processes. And here's what it looks like. So observe how the orange curve changes, the blue remains constant. And these paths here basically represent the paths that different particles take under the influence of these two processes. And as you can see here, the orange paths are different from the blue, obviously, because that's how you get there. And the Gale divergence that I'm talking about is basically a Gale divergence between the probability distribution over these paths. And that's what I meant by saying that the Gale is a Gale divergence between path measures. Okay. So the effect of this reverse process here is that it's adding back the information that was erased in the forward process. So you can think of the reverse process as a non-equilibrium process, which basically drags the system away from its preferred state, which is defined by this native dynamics of the system, right? It drags it away from that preferred state onto PD. All right. Okay. So S dot is the scale divergence, which is why S dot is a non-negative number because that's a property of the Gale divergence. But I can do something else interesting with this, which is that I can basically marginalize over all time steps except the final time step here. And I can basically derive the following inequality, right? So this is one of the Jarzynski inequalities, which were popularized or which kind of came into view during the late 90s and early 2000s. This particular form of the Jarzynski inequality can be found in this paper. I would argue, though, that there is actually nothing in these Jarzynski relations that was not already known to Schrödinger, right? Okay, so I'll kind of write the results again here. I will point out that for these two stochastic differential equations, it is actually fairly straightforward to write a expression for the scale divergence, and it basically looks like this. All right. Now, to quickly summarize
Wait, is
everything, yeah.
are R and F here treated as okay, wait, no, never mind, sorry.
Okay.
Um,
I'm sorry.
makes
So
sense.
I'll point out the following. R is again a playback of the forward process. So R basically knows about how PD gets converted to P equilibrium, right? And this information enters R through the drift term, because the drift term, as you know, is this from the literature on diffusion models. And I basically put a little arrow about the P to indicate that this is grad log P computed from the forward process. And when R is applied to P equilibrium, it's basically injecting information to convert P equilibrium back to PD. Okay. I'll also do one more thing here. So let me actually switch to a slightly different view. I'll just replace the stochastic trajectories with the shape of the probability distributions at those intermediate times. And keeping everything on the slide fixed, I will make one small change, which is that I'll change the underlying dynamics of the system, which is this, to this. So I replace my forward drift with a new drift, which I call the control. And if I do that, the only change to these expressions is the following. So this is something we'll keep in the back of our head for the next few minutes. If I minimize this, I have to do that by basically setting U equals BR. And if I set U equals BR, then basically both processes become identical. Okay, we'll come back to this in a few minutes. All right, so finally, with all that physics done, we are ready to discuss diffusion models, right? So in diffusion models, the equilibrium distribution is some sort of Gaussian, and a sample from that Gaussian is just some random noise vector. And if I know a way of converting P equilibrium to PD, I can apply that process to my noise vector, and I can convert it into something more structured, like an image. Of course, the problem is that I need to understand how to convert P equilibrium to PD without knowing what PD is, because all I'm given is basically a set of samples from PD. And this should kind of remind you of the problem that we started with, right? But here is the interesting bit, which is that the reverse process is just a playback of the forward process. So all I need to figure out the reverse process is to basically do a bunch of simulations of the forward process. So I can take a sample, one of those given samples, and I can basically run the forward process on it cheaply, right? This is easy to do on a computer. And in fact, I can do this for all the given samples. And so I just propagate my samples to random instance of time. And as I do so, I basically get an idea about where the particles ought to be in the reverse or the generative process, right? So this is me propagating each sample just once. So in other words, this is one training epoch, but I can actually repeat this multiple times. And if I do that, then slowly a picture emerges about where my particles statistically ought to be, right? And this kind of shape, in kind of sideways Y shape that appears, is basically what's called the Schrödinger bridge, because it's the thing that interpolates my PD and P equilibrium, right? And I have a neural network kind of sitting on the sidelines observing this process to kind of figure out, again, where the particles should go at each instant of time. In other words, I'm basically trying to figure out these channels that take me from PD to P equilibrium, so that to generate a new point, I just need to kind of travel back along those channels and I go back to PD, right? This is, of course, a very qualitative description of what happens. When you actually want to train a neural network to do this, what you do is you assume a reverse process that looks like this, where U is parameterized by the network, right? And you consider essentially the following loss function, right? Which is now the KL divergence between your approximate R and the output of the neural network, or the process simulated by the neural network. The gap between the true underlying distribution and p theta is upper bounded by this object here, which is the scale divergence. And therefore, if you want to make this scale as small as possible, we can do that by kind of tightening this upper bound as much as we can, right? Which is what happens during training. But from the entropic point of view, what really happens is the following. So you have some U theta that's initially not aligned with R. And then during training, what you're really doing is you're adjusting your U theta to match R. Or in other words, you're basically having the neural network remember all of the information that it needs to basically drag the system away from its equilibrium state onto PD, right? And so this is what I call neural entropy. It's basically the amount of information stored in the network, so it can kind of remove the entropy from the system. All right. Okay, so let's look at a couple of practical implications of the statements I just made. So first of all, we can think about how we want to parameterize the control. The goal is to try and get a reverse process drift that looks like this. So it might seem that the most obvious thing to do is to just parameterize your U theta to have exactly that form. And if you make the substitution into this loss function, you get what's called the score matching training objective, right? But there is a problem here, which is the following. Suppose I disconnect my network. Okay, so I disconnect it here and I disconnect it here. Now, whatever remains here is the thing that I want to interpret as some sort of entropy measure. But let's consider the following scenario. Suppose I replace my PD with a corner case where PD is just the equilibrium distribution itself. So I do this. Okay. The problem is that grad log P is non-zero in some region of space. And therefore, this entire object is actually going to be some positive number, even when you're trying to convert a distribution to itself, which does not make sense, right? So if your distribution actually does not undergo any change under the diffusive process, then the entropy produced, or in other words, the information erased, should be zero. And this object actually does not reflect that. And there's a much more detailed explanation in my paper about why this doesn't happen. But we can kind of fix this quite easily. So all we
It can still be
need,
zero if you learned it correctly, or am I misunderstanding?
no,
Wouldn't the
no, so
optimal
that's
score
with the
just?
network. So with the network disconnected, right? I'm trying to find the gap without the network contributing.
Oh, I see, I see, I see.
Yeah, yeah,
Um, oh, I see. Okay.
yeah. So
Sure.
kind of the
Right.
gap between the orange and purple path measures. Sorry, orange and blue
Gotcha.
path measures.
Okay.
Yeah. So all we need to do here is basically take the control and parameterize slightly differently, which is to say that remove the minus sign from there, right? And if we substitute it here now, we get basically what I refer to as entropy matching in the paper, but this is just diffusion flow matching, okay? Um, if I disconnect my network now, then what remains is actually the thermodynamic entropy generated in the forward process. So this does not suffer from the same problem. If I start with a distribution and which is the equilibrium distribution, this thing is actually just going to be zero. So this is honest to God entropy measure. Okay. Um, Furthermore, so if I take u theta equals bf initially with my network not contributing, then u theta and the forward process are identical, which means that u theta basically starts at this point f on this figure. And then during training, I basically just start from f and slowly learn how to do r. Oh, yeah. So that's a good question. So entropy matching corresponds to basically what's called flow matching in the diffusion setting. So I should be careful here because, so I refer to this as entropy matching in my paper because honestly, I wasn't aware of flow matching when I was doing this work. But also in the flow matching paper, there are many things that kind of fall into the umbrella of flow matching. So they usually draw like the straight line trajectories and kind of, take an average over all of those straight lines. Uh, Diffusion flow matching is when they just use the diffusion paradigm, but then they parameterize the control term like this so that their loss function looks like this. Um, so this is kind of, I think, if you look at Yaron Lipman's flow matching paper, this is, I think, basically what they start with before they generalize into these straight lines and conditional optimal transport and all that stuff. I hope that answers that question, Rob.
Okay, would you mind going back just back to the score matching? And I just want
Yeah.
to, it wasn't totally clear why this is not still zero. Or I think it might be. I just need to stare at it one more time if
Yeah,
that's
yeah.
okay.
So in the entropy matching case, it was clear that you were starting at F and then closing this gap, right?
Yeah.
So with the network initially untrained or like completely disconnected from the system, there is a gap between the forward
Oh yeah,
process
yeah, yeah.
and whatever the network tries to do, because the
That
network
makes
has
sense.
to, yeah.
I was gonna say the thing that confused me was when the case where you're just like applying your forward process to something that's already like you're just staying at equilibrium and just adding Gaussian noise to
Yes, yes,
like you have Gaussians at both end, and
correct.
then the claim was that some loss was not zero. It seemed
Right.
like the forward and backward dynamics were the same, so it seemed like it would be zero, but it wasn't totally. I think that
Uh
was like one slide back or maybe one
yeah,
slide
yeah.
forward. I'm not totally
So
sure.
what I was trying to argue is the following. So let's kind of look at score matching here.
Right.
Okay. So forget anything about disconnecting networks. Okay.
Okay.
If my data distribution is same as the equilibrium distribution,
Right.
the scores learned by the network are not zero everywhere, right? There are some
In the
regions in,
sense they're not perfect.
not because they're not perfect, because this grad log P is actually not zero in some regions.
Sure. Right. But if our network learned it, wouldn't this difference be zero? Or I think maybe I'm
Ye-
missing the point somehow.
Yeah, yeah. If the network learned it, the difference would be zero. But the point is that the network shouldn't have to learn anything to convert a distribution to itself.
Oh, I see. Okay. Perfect.
That's the
Yeah.
point.
I see. I'm with you.
Yeah,
Okay.
exactly.
I appreciate the clarification.
Uh, Completely fine.
So
Um,
you just want to build that inductive bias into your actual divergence is the point here.
Yeah, yeah. So, well, for me, I want to be able to interpret this loss function physically. That's my
Mhm.
primary motivation, but I'll show you an experiment a little later where I show that because of this fact that the score matching loss actually is capturing some unnecessary amount of information, it actually trains more slowly. And I don't know if this fact is actually appreciated a lot um, in the literature. I don't know. Again, I'm not like a hardcore ML person. If this is known in the literature, please tell me. But I do point this out in one of my papers.
And then we go to the entropy matching loss, and this issue goes away because we parameterize as
Yeah, we parameterize correctly, and um, we get this loss that basically when we don't have the network contributing, it just looks like the actual thermodynamic total entropy, like the physical entropy, right?
mhm.
And that thing is in fact zero when you try to convert a distribution to itself. So if a
Okay.
network were to try to learn from this loss function, it would have to learn nothing to convert a distribution to itself.
Oh, I see. So you reparameterize that the backward process looks like forward plus some contribution. so that
Exactly.
in this equilibrium case, your forward and backward dynamics are actually given by the same drift. So you just is it
Exactly.
okay? All right, I'm with you. Sorry, I
Right.
appreciate the going over that
No,
again.
it's completely fine. That's yeah, that's exactly. I think I hope this is also clear to everyone else. Yeah, please ask questions if. Okay. All right. Uh, okay. So this is, like I said, you're basically starting exactly like you said, the reverse process, with the untrained network or the disconnected network basically looks like, it looks like the forward process, and then it slowly learns how to do the reverse process by kind of closing this gap, right? So it's
Couldn't
kind
you
of
argue
absorb.
that? Oh, sorry, keep going. I
No, no, go ahead,
apologize
go
for
ahead.
interrupting. I was gonna say, couldn't you argue that if I were to like write down, like if I were to just prescribe some arbitrary forward process
Uh-huh.
BF, and then I write the time reversal as like BR minus sigma squared times my score function, that I would end up and I put that into here, I would sort of get the same thing, just because the time reversal, the drift in the time reversal is just the same as the forward drift.
Do you actually mean to say BR minus sigma squared? Or BF minus sigma squared
Or
term?
like if I guess the claim is that if I have some arbitrary forward process, like I guess
Hmm.
in this case it's like BF dt plus sigma
Yeah,
ddt, and
it can be anything except that the forward process has to have this confining property. In other words, the forward process has to have a stationary state. If you take something like an Ornstein-Uhlenbeck process and flip the sign of the drift term, this wouldn't happen, right? Because it doesn't have a stationary state. So when you
okay,
say any drift term, it basically means you're constrained to have a drift term that has some sort of equilibrium. Uh, will give you
I
some
see.
equilibrium state. Yeah.
Okay. I see.
So
So,
this is, I
but
mean,
at the end of the day,
really,
we're regressing the drifts here instead of
yeah.
the scores.
Uh, I, yeah. So the thing that you learned here will not be the score. It's the score plus some term,
Okay. All
which
right.
kind of
I apologize. I don't want to take us on too much of a tangent.
no.
Let's just keep
Let's
going.
actually maybe we can come back to it at the end. But yeah, okay. So moving on. So I want to kind of call back to a fact that I mentioned earlier in the talk, which is the following. So I pointed out that by choosing different forward processes, we can basically make this gap smaller. So I told you that if I were to take a gentler forward process, the corresponding playback would also be slower, and therefore the gap between the forward and reverse process would be smaller, right? And this is precisely the gap that corresponds to the information that the network needs to kind of store inside it, right? So if the goal is to reduce the informational load on the network, then we should be choosing a forward process for which this purple line is actually as small as possible. Because in the context of diffusion models, a neural network is just a kind of glorified memory. It's just absorbing information and then kind of reinstating the information during the generative process, right? But there is a kind of interesting tension here, which is that if you make the forward process too slow, then basically the amount of time it takes for you to, uh, you know, equilibrate, which is also the amount of time it takes for you to reverse, is going to be longer. So if you also insist that you want to finish this whole thing in a fixed amount of time, then there's a limit to which uh, how slow you can make the forward process, right? So that's the tension. You want to make it as slow as possible, but you only have a finite amount of time to finish kind of homogenizing your data distribution into this final prior distribution. And because of this tension, there is some sort of sweet spot. So there is a optimal point at which the arrow is as short as possible. Okay, given the constraint that you have to do this forward process in a finite amount of time. And that minima is basically related to the L2 Wasserstein distance between PD and P equilibrium. This has been observed in other papers also. But the interesting bit is that this is what's called the thermodynamic speed limit in just physics literature, which is what is the maximum speed at which you can move given a fixed amount, given a certain finite amount of time, to transform one distribution into the another at minimum entropy cost. Because that entropy cost is, in our context, the thing that is being absorbed by the neural network. All right. Okay. So let me kind of give you the big picture here. I have essentially what I call a diffusion cycle. So initially, the first part of the cycle is where I basically simulate all my forward processes from the samples. And as it does so, my network is slowly learning how to approximate the reverse process. And that's when all of this entropy generated is absorbed by the neural network. And during the generative step, it's basically applying that information to do the generative process, right? And this is a very idealized cycle, as you can imagine, and as it is true in all of thermodynamics, there are going to be losses, and therefore you don't truly learn S dot, you learn something less than S dot, and you apply even less than that when you're doing the generation, okay? Now, this process of applying information to lower the entropy is reminiscent of this thought experiment from physics called, called Maxwell's demon. So the essential lesson from Maxwell's demon is that, okay, this is kind of annoying, but the essential lesson from Maxwell's demon is that information negates entropy, right? So if you know information about a system, you can basically apply it to lower the entropy of the system. So I won't kind of go through the whole thought experiment again, but that's the main point. All right. So I'll show you a couple of experiments. The first experiment, here's how you understand this graph. So all of these experiments were done with synthetic data where I knew what the true underlying data distribution was. So I know what PD is. And P theta is the reconstructed distribution from my diffusion model. So I take the KL divergence between the PD and P theta, right? And I plot it against various values of neural entropy. So what I'm doing here is I start out with different distributions, which means that the entropy of conversion or the amount of information the network needs to remember is different for reconstructing each of these distributions. And I basically start with a small amount of neural entropy, and I gradually work my way up to more and more complicated distributions, which have higher and higher information content. And I do this across multiple dimensions. So this is at 4 dimensions, and this is at 8 dimensions. Ideally, if you had everything working perfectly, the KL divergence should always be 0 because the reconstructed distribution would be exactly the same as the underlying distribution. But that's not what happens. What we see is that when you ask the network, which in all of these experiments, I'm using exactly the same size of the network and with the same structure. So the network has the same basic memory capacity. So what you see is that as I ask the network to remember more and more information, the performance of the network basically degrades, right? Which actually makes intuitive sense.
So just remind me,
Yeah.
I was going to ask, so SNN is just this like path divergence given by your learned drift.
Right. It's the purple line. It's that purple arrow, like the little gap.
Okay, right. And so did you this is like these, so these dots, did you you were training your model and then kind of you stopped it during training and kind of calculated as it was getting
No.
better? I
This
guess.
is with different divergences, but the next graph I'm going to show you is exactly that. I stop it multiple times during training. So this is with
Okay.
different distributions. That's how I basically changed the entropy. So I took different distributions where the size of the gap was different for each of those distributions, because it also depends on your data itself.
Okay. Just to make sure I understand. So you start with some PD, some choice of PD,
Yeah, like a
and
Gaussian mixture. Yeah, like a Gaussian mixture. Yeah.
then you do, or just in order to like even or you just initialize some random network and then observe what its SNN is and then plot it.
No, no, no. I
Or,
so SNN is calculated completely in data space. So
oh,
it's the amount of information that you need to or that gets erased if I start with a particular distribution and I convert it into some generic initial distribution. So
I see. But it's yeah.
I take these various PD and I convert them all into the same distribution and I compute uh, by Monte Carlo methods, what is the entropy of the transformation, which I then say that that's the amount of information the network needs to remember.
Oh, this is a function only of your forward diffusion process. There's nothing learned about this.
This is only of the forward diffusion process. This is the learned object. This is the learned behavior because the
Oh, I
PD,
see. I see. I
yeah,
see. I see. Okay.
exactly.
Right. So
So
this is
you
like the
have to
same
think of
picture you were showing where you simulate the Schrödinger bridge and then like
yeah, exactly,
compute the. Gotcha.
exactly.
Okay. Perfect.
Right. So this is you can think of this as a knob that I adjust and this is kind of like the performance of the network.
Perfect. Okay. Makes sense. Appreciate the
Yeah,
clarification.
yeah. Uh, And then I basically alluded to this fact that score matching, it appears as actually forcing the network to remember more information than it needs to, as we saw with the example of having to convert a distribution to itself. And you see this when you look at these curves. So I'm plotting the same KL divergence here, but now as a function of the number of training epochs. So what I do here is I train for 10 cycles. I take a particular PD, I train for 10 cycles, and I look at the performance of the network. I train for another 10 cycles, I look at the performance of the network in terms of how good the reconstruction is with respect to the true underlying distribution. And you can see that with score matching, I need to train for more and more epochs to kind of get the same performance as I would get from entropy matching. Uh, and it's entropy matching basically gets the correct or converges to the kind of answer in like order 10 epochs. Whereas score matching, because it somehow has all this additional information that it needs to remember, takes much longer to uh, learn.
Hmm.
Okay, so um, I can stop here, but I have like one more piece to it, which probably takes like 10 more minutes. I don't know if I'm over time or if I can have 10 more minutes
I'm happy to
because,
stay if you have time. Um, and
yeah,
anyone else, welcome to stay. Welcome to leave as you please.
okay. All right. So I will,
We have a question from Michael about, can you explain the difference between score matching and entropy matching curves with the grad term?
with the grad, so can I actually circle back to that at the end of the talk? Because I just want to like finish this last bit. Uh,
Yeah, sounds good.
yeah, okay. All right. Thanks, Michael. All right, so the application of all of this stuff. So I'm super excited about this entropy interpretation, not just because it's some sort of like theoretical tool, but it actually uh, allows us to explain many of the behavior of diffusion models that were not previously well understood. And I'm working on several projects to kind of tap into that insight. Um, but one of the applications that was kind of immediately obvious from some of the calculations I did is the following, which is to use a diffusion model as a neural density estimator. So let's kind of go back to this problem that we started with, where we, wanted to basically understand what the underlying distribution was, given some set of samples. Now, we've talked about how a diffusion model would go about doing that. But having reconstructed the distribution, right, can we then evaluate the probability, or I shouldn't say probability, can we evaluate the density at a new test sample, which I'll call X prime, right? So what is the density of the underlying distribution at this new X prime? So this is the question. Of course, the problem is that diffusion models basically learn scores or something analogous to scores in the entropy matching case. So there is this we basically learned this grad log p kind of term, and we need to try and figure out how to extract just the p or just the log p from that. All right. The conventional way to do this that is already discussed in literature is what's called the probability flow ODE. I mentioned to you that, if you start with a random sample in PD or, at this plane, I can basically propagate it to some point in the prior using my learned scores or whatever is the analog in the entropy matching case. And I drew these smooth lines to do so, right? But you could ask, well, how do you get these smooth lines from these stochastic trajectories? And the reason is that if you kind of play around with the Fokker-Planck equation for this ODE here, sorry, SDE here, you can convert it into an ODE that looks like this, right? And therefore, the corresponding reverse flow, so this is going to be a smooth flow because it's an ODE. The reverse flow is exactly the same thing, but with a negative sign, right? And if you do a little bit more math, you can actually show that the log p evolves also in a flow-like equation given by this, right? And therefore, if we start with the x0 prime here, which is uniquely mapped to some x prime here, you can instead replace it with x0 prime and log p equilibrium evaluated at x0 prime, and then use these two ODEs to kind of flow back to this value here, okay? And then you can extract from that the log PD evaluated at x prime. Of course, this is a very idealized case, right? Because you don't know what the true reverse drift is. You only have an approximation to it from the neural network. And therefore, if you apply the imperfectly learned reverse drift, you're going to accumulate some error in this process. And in my paper, I basically have this experiment where I, again, take something like a Gaussian mixture in 9 dimensions, I believe, in this case. And I know what the actual log PDs are, and I plot the reconstructed log PDMs at some other random points with my diffusion model, and I compared the two. So the orange line is like the ideal curve, and the kind of the blue line here is the estimated value from the diffusion model, right? Okay. Now, here is a problem with the ODE approach, which is that it is an iterative approach, because you know that solving an ODE is a sequential operation. So you need to compute the value of the variables at the current instant of time to be able to predict where it goes in the next instant of time and so forth. So it is structurally a kind of iterative operation. And therefore, you need to kind of time step through each of these curves to get this answer back, right? And so what I was trying to do is figure out a way to do this without doing that iterative step. And here is how I do it in this paper. So I took some inspiration from quantum mechanics. Here is how it works. Suppose you have some random point on your equilibrium distribution, which I'll call x1 here. There are many ways of starting from x1 and going to your test point x prime, okay? And I denote some of those paths in orange here, right? Now, the probability of starting at x1 times the probability of all ways of going from x1 to x prime is going to be a contribution to PDX prime. But that's not all. I could have started from another point and also travel to X prime along many different paths. So I should really sum up the probability of starting at different points on my equilibrium distribution and the probability of all the different ways I could have started from each of those points and ended up at x prime to compute the probability of x prime, right? So this is all under the reverse process dxt, right? But here is where the problem lies. This probability is very difficult to compute. We don't have like a nice expression for it. But we can use the entropy picture and observe that each of these paths is basically adding some amount of information as it converts each of these noise vectors to x prime, right? And we also know that the Shannon entropy of the distribution PD is given by this expression, which means that minus log PD evaluated at a given x prime is just the amount of information for that particular x prime. In other words, it's the entropy of all paths that lead to x prime. The second interesting fact is that we can, since the reverse process is just a playback of the forward process, we can just figure out where the what these orange trajectories are from just simulations of the forward process. So combining these two facts, we can actually derive a simple expression. And I'm not going to explain all parts of this expression. I'm just going to kind of give you a little bit of intuition. So this is the expression from my paper. The information about the prior basically gets encoded in this expectation value here, which I call the prior entropy. The information about the probability of the different paths becomes encoded in this part here, which is called the path entropy. And if you add the prior entropy to the path entropy, you get the entropy contribution of that single test point. The nice thing about this is you don't actually have to simulate all of these paths to evaluate this expectation value. Because you know, if you are work with a diffusion model, that one of the great advantages of a diffusion model is that you can avoid simulating these stochastic trajectories if you work with a transition kernel that is something like a Gaussian, right? Because then you can just randomly sample these paths at any instant of time. And therefore, these expectations values can just be evaluated in basically a single time step. And so it avoids the iterative cycle that you need to go to evaluate the densities in the ODE approach by basically having a super parallelizable formula. So I do some very early timing experiments. So this is the orange curve here is the time taken to compute the log P's with the path integral approach, and the orange curve is the PFODE. So I deliberately had the path integral slowed down to give its worst possible performance. And you can see that it's roughly 2x faster than, or at least 2x faster than the ODE approach. What's also interesting is that there is not any variance. So the variance of the PFODE approach in computing the log P's is because when you solve an ODE, the solver actually takes adaptive step sizes, and therefore the time it takes to actually solve the ODE depends on the exact trajectory that you take, which is what creates this large variance. All right, so that was, again, a very quick and qualitative description of how this algorithm works. I would refer you to this paper if you're interested in more information. I'll just leave a kind of conclusion slide here. Please feel free to email me if you want to discuss more or if you have any more questions. But I will take more questions. I think Michael had a question about the entropy term, which I'm happy to come back to, but I also want to give opportunities for other people to ask other questions if they have any.
Well, thank you so much, Akhil. And maybe we'll start with Michael's question.
Okay. All right.
Where's Michael? Michael,
Uh,
are you still there?
so yes.
Oh,
So can you
okay.
explain the difference between score matching and entropy matching curves for the grad term? Yes. Okay. So I assume that by curves, you're actually referring to the performance curves. Let me go back to that. And all right. Okay. Okay, good. So take the difference between those two performance curves and see if the grad term from this. I don't think it's the grad term that's causing the problem. And actually, I discussed this in much more detail in my paper. So the problem is really a problem of measures. So again, um, uh, thermodynamics is just probability theory, which is just measure theory. So everything that I talked about today can actually be understood in terms of path measures in a more rigorous way, which is something I attempt to do in my paper. The difference really is coming from that flipping of the negative sign of the BF term. So I had that somewhere here. So here there is no sign for the BF term, and here there is a sign. This sign is actually what creates that issue. And you can actually trace it back to the difference between the performance. So in other words, when you have this minus sign here, the neural network has to basically fight this thing, this incorrect sign on the drift term, and also pump information into the distribution to kind of mold it back to the distribution. So this erroneously signed term, when you apply it to the equilibrium process, makes the equilibrium process blow up, because this equilibrium process is a stationary state when you have plus BF here or plus BF here, right? If you flip the sign of, think of like an Ornstein-Uhlenbeck process. If you flip the sign of the Ornstein-Uhlenbeck drift term from, minus to plus, then the equilibrium distribution is no longer a Gaussian, it just gets blown up to infinity. So the neural network basically has to fight that tendency and add information, which is why there is a greater information load on the neural network. I hope that answers that question. There's a greater discussion in my paper. Okay. There is
Sorry,
another.
what is your proposed entropy matching parameterization? Does it just use the correct time reversal of the equilibrium process?
Yeah, so the entropy matching drift term basically looks like this. So the whole point is that in the absence of the network contributing, it should just look like the forward process. And that way, with the network connected, you're just ensuring that it's adding only the information that's needed to turn the equilibrium process into the data distribution.
I think I'd like to think about it as like a difference of scores then for the target process versus the reference process. That's what epsilon's learning.
This thing?
Yeah. So like you kind of have beef. Maybe not. Okay, but that's a good explanation. Yeah.
Okay.
Wait, so this whole discussion of like the sign is flipping in your forward process, wouldn't you sort of want it to flip if you're going backward? Like if it's an Ornstein-Uhlenbeck process and my forward drift is saying like kind of go towards zero, or like if I'm at X, it's kind of like kind of telling it to go toward the the mean of kind of whatever Gaussian you're trying to converge to. Then it
If
seems like
you
intuitively, if I was trying to go backward, I would want to kind of go in the
Right.
opposite direction to kind of undo that.
Right. What breaks the
It doesn't,
intuition is the
yeah,
noise. What breaks the
the
intuition is, if
noise,
you had zero noise in the system, you're exactly right. So if you had zero noise
right?
in the system, then you basically have, something like BFDT being your forward process, right? And the way
Okay.
to flip that is to just change the sign of the reverse, change the sign of the drift term. But what breaks the intuition here is that the equilibrium distribution is what you get because the drift and noise are kind of fighting each other.
The drift and the noise are fighting each other.
That's how you get an equilibrium
Um,
distribution, right? The noise wants to basically blow
right,
things
right,
away to infinity, and the drift contains everything. So
right.
if you flip the sign of the drift term in a diffusive process, then both noise and drift are trying to blow things up to infinity, and you don't have an equilibrium distribution at all.
If I flip, say again, if I flip it, they're both trying to go to infinity, and um,
Take the particles to infinity, I mean.
sure. But like you could imagine that locally your drift wants to move it out from the center, but you know, okay, well, yeah, okay, I see. I have to think more about this, but I
Yeah,
see where you're coming
yeah,
from. It's
yeah. It's it's
um,
it's this kind of, yeah, you have to think of it as a interplay between the two things. I think there was a question in chat, relation between manifold hypothesis and entropy matching. Okay, what's the idea? Okay, this is actually something I'm actively working on right now. I don't want to, um, so I have some collaborators. So I don't know how much they would want me to talk about this. But um, essentially, the point is that data lives on lower dimensional manifolds. And that has interesting consequences in terms of entropy production. So I'll just say that for now. Uh,
Uh, just maybe I don't know if it's connected or not, but I've been thinking about hierarchy of like abstract concept in the light and space. It's like when you diffuse
uh-huh.
uh, information, you kind of go up the level of abstraction, kind of. There is some kind of analogy. Do you think it's kind of promising or possible?
That's I've never thought of it like that. I yeah, if you could send me some references, that'd be great because yeah, most of the stuff I'm doing actually just still treats the neural network as a black box. And tries to, so in that way it's kind of a callback to the early days of thermodynamics where people were making steam engines without really even knowing that atoms existed. So in some way I'm thinking of the neural network as this black box that kind of remembers things and trying to characterize its information storage capacity. So I haven't really thought about things from the perspective of I don't know, like the latent space, like the network weights and so forth, but it is something I would like to do. So I don't really have a good answer for you, unfortunately.
I'm
But
just
I'd be
trying to think
interested if you
about
want
this.
to. Sorry, go ahead.
Yeah, kind of inspired thinking like in kind of reasoning when you move from big picture to and then details, just going to abstract concept space. It's like and add more details.
Uh-huh.
So it would be I'm like it's very intriguing if you could kind of interpret it
Yeah, yeah. Okay,
differently.
okay. I think so. There is, maybe I'll make this one comment, which is that people have noticed the connection between diffusion and what's called renormalization group flow in physics, where in RG, basically you kind of integrate out information at different scales. And in diffusion, that is kind of happening where, just if you stare at a picture that is progressively getting noised, you notice that the low frequency details or the long wavelength details uh, are the ones that get erased at the very end. And so that's one fact. The second fact is that you can think of a diffusion model as a infinitely deep variational autoencoder. So this is kind of coming from the neural ODE picture, right? And if you take that perspective, then you can map each layer of this infinitely deep VAE to a particular scale of the features getting erased. So there is something there for sure. I, I'd be, yeah. But I haven't thought about it beyond just kind of having this rough intuition for it.
Okay, thank you.
Do you have intuition for how, or keep going, Alec? I'll let you
Yeah,
finish your
please,
question.
please.
No, just it's a kind of another analogy. It's like the most abstract object is probably a sphere, and then you add some kind of vertices, and you could move from like to arbitrary object from the most like generic object.
Uh-huh.
So it's maybe like superficial, but that's kind of.
What was the last part?
It's like you could approximate any object, any picture. It's like also some kind of with a sphere, right?
Uh-huh.
And then you could just deform it gradually and end up with any object eventually. Just adding like stretching it, adding vertices. It's a kind of another process of moving in. That's kind of similar.
Okay.
Maybe it's relevant.
Okay. Yeah, it's interesting. I don't have any more thoughts on it right now, but yeah, if you have some literature in this direction, please let me know. I'd be happy to take a look at it. But yeah, I don't have any more.
Not that many literature, but the kind of connected to the manifold idea also, right?
Okay. Yeah, I was thinking, yeah, I was thinking about the fact that real world data seems to fall on a manifold, on some sort of lower dimensional manifold anyway. Like even if, okay, forget the manifold of the internal parameters of the network, but or sorry, I shouldn't say that, but I'm saying that there, for example, if you take like the MNIST training data set, and if you were to do some analog of PCA on it, or if you were to try and compute eigenvectors at some point of the data space, you find that it's a very low dimensional manifold. That's kind of what I was alluding to.
Yes. Okay. Yes, I see.
Okay. Any other questions?
Yes,
I know it's
maybe
getting
I have a
late, so I
question.
don't want to prolong. Oh, Danny, did
Yes,
somebody?
sorry. It's
Go for
maybe, hopefully it's a quick question. So you said that with your framework, it is possible to, I guess, choose the noise distribution so that the difference, the gap between forward and reverse process will be minimized, and hence there will be less strain on the network. But my question is it really good for the generative capabilities of the network? Like the process of learning will be easier, but what are the implications on the diversity and I guess like the creativity of the network?
That's a great question. So this is actually a detail that I kind of skimmed over. So I want to go back to this picture here. Okay. So, this looks like a cartoon, but this is actually an honest to God simulation of the forward trajectory. So this is actually a diffusive process. This is an Ornstein-Uhlenbeck process, right? And notice that you have these funnel structures that emerge, right? So you have the bridge basically kind of almost falls into these narrow channels at the very end of the generative process. So the generative process runs in this direction, and because of kind of the sparsity of the training data, it creates these kind of funnels in the bridge. And people have indeed studied these shapes, or they're beginning to notice that there is this like localization effect that happens, where if you run the generative process for a while, then basically your generated image or whatever it is actually starts resembling some of the training data. And that's because of these funnels. Now, the way I think people tackle this in the literature is what they do is, let me see here. Yeah, they take the So I put a little star next to the training loss. And one reason I did that is because this is not the actual training loss or the elbow that people use when you actually train diffusion models. So you multiply this prefactor with something else, and the effect of that new prefactor is that it basically cuts down on the amount of information going into the network from this region. And so the whole point of doing that is to kind of confuse the network just enough that it allocates probabilities to points that interpolate these red points. So the generative process, once it gets here, it kind of gets confused about where exactly to go, and therefore it actually ends up falling into some point in the middle. And there is an interesting tension here because you don't want to remove too much information from here, because then it becomes less accurate. It doesn't learn properly. But if you allow the network to remember too much information from here, it doesn't generalize. It becomes kind of hyper localized on these samples. So that is kind of another thing that you can understand from the entropy perspective. And as to the question of whether you want to lower the entropy across the whole process, certainly it is true that if you make your line straighter, if you make your forward process more and more, like rapid. So for example, if you think of like the flow matching with straight lines, you can almost think of it as a limit where it looks like the rapid reversal process in the Schrödinger thought experiment I showed you before. Therefore, I would expect that some of those processes where they try to make the line straighter are actually entropically worse for the network. So the price that you pay for generating things faster. So you want to make those lines straighter because during the generative step, you want to solve your ODE faster, right? That's why people try to make those lines straighter. But the price of doing that is that you're asking the network to basically remember more information.
Yeah, thank you for elaborate answer. I think maybe an interesting complement to you is when diffusion model is considered as a Hopfield network or an energy-based model. It's not a very popular view, but maybe for you as a person coming from physics, it may be interesting.
Yeah, I haven't really delved into energy-based models, but I do want to. It's kind of on my laundry list of things to look at. But thanks for recommending that.
Thank you.
All right.
So from the practitioner's perspective, so how does that kind of fits in your compute, like in the CPU time versus if you're planning to for a CUDA-based GPU time? So does that also kind of so how do you make it faster with respect to the last slide that you had? So with respect to the images, so like and based on the dimensions of that image, so and the distribution of that data that you pointed towards, plus the different kind of distributions that you can adapt your data to. So I was just wondering, from a practitioner's point of view, does you have taken that into account too?
So I haven't done any kind of calculations with, for example, at the level of looking at the level you're mentioning, right? At the level of
Okay.
like, how many GPU cycles or memory or whatever it takes.
Mm-hmm.
But I would, again, just from a pure physics argument, I would expect that if you can train your network and your network learns in like an order of magnitude fewer epochs, right?
Mm-hmm.
Which is what you saw with like entropy matching versus score matching. Then that means that you can spend that much less time training your network,
Mm-hmm.
right? And therefore, again, from a very back of the envelope calculation kind of way, I would expect an order of magnitude reduction in the amount of energy required to compute. But the more kind of like detailed, what's happening at the network level thing, that is something I'm super interested in. again, I want to do it for, something like CNNs and more practical networks, because all the experiments I showed you were done with like simple MLPs and so forth, because I
Okay.
was just learning like Gaussian mixtures.
Mhm.
But yeah, it is also something I'm planning to do in the future, and especially in terms of like density estimation. So the density estimation algorithm I introduced in my paper, that's the first time I actually started worrying about like, how much time it takes to compute and so forth. So that there is potential there for, some sort of like implementation cleverness to optimize it.
Yeah, you kind of like half the time with respect to the ODE that required there. So yeah,
Yeah.
that's like, yeah, cool.
All right.
Alrighty. Are there any more questions? Anyone else? I have one closing thought, which is
Okay.
just I was curious how much which of your experiments were with Ornstein-Uhlenbeck processes and which were, or basically I'm just thinking like, to what extent does this reparameterization exploit like what the actual reverse process looks like in the special case that you're trying to reverse an Ornstein-Uhlenbeck process? Because you could argue that, or yeah, keep going.
I was going to say that if you don't have a drift term, then entropy matching and score matching basically look like the same thing, because there's nothing to flip a sign for, right? There is no drift term.
Mhm.
So that said, the reason we use Ornstein-Uhlenbeck processes for diffusion models is because it allows you to solve for a finite time transition probability that has a closed form expression, and that's the thing that
Right.
allows you to do avoid doing all these simulations.
Right. So
Yeah.
I guess what I'm trying to get at is kind of that like it seems like one of the reasons that this is so clever is that like when you get close to zero, kind of the relative sizes of this, I guess if it's, if we're working with an Ornstein-Uhlenbeck process where the forward is like kind of has an over 2 factor, like sigma squared over 2 times x.
Mhm.
When we get close to zero, the score starts to just look like x. And so this whole reverse drift term just ends up kind of looking like BF itself. And so it's it's almost a good parameterization to just say it's almost BF. But at very high
Right.
noise values, maybe this approximation is less
That's
faithful.
that's exactly why S dot vanishes. So, like entropy. So physical entropy. So I had this expression for the total entropy, right? That vanishes
Yeah.
exactly because of that reason. Because the at the stationary state, it just looks like a Gaussian. And if you take like the log of the Gaussian and take the derivative, it just looks like the drift term.
Right.
But that is generically true, not just for Ornstein-Uhlenbeck processes, but for any process that have like a equilibrium distribution. So any confining potential.
Right. Sure. That makes sense.
Because e to the power minus potential over noise strength is basically the form of the equilibrium distribution. And then grad of the potential is just the force, the drift force.
So within closer to time equals 1, maybe like a more generic parameterization is like, or I guess it's definitely clear that entropy matching is a better formulation close to 0, but maybe there could be some argument that score matching might be more accurate close to 1 or something like that. Have you like, is that?
Score. Okay, so both of these have another problem. There's a
This is very vague. I'm not.
No. There's a
Yeah.
very famous singularity sitting at time t equals 0, which doesn't go away in either score matching or entropy matching. And this is related. So you have, when you compute the actual expression for the score, it looks like x minus x prime over sigma squared, where x minus x prime scales as sigma. And so you have sigma over sigma squared, where sigma goes to 0. So you have basically a 1 over 0 kind of singularity sitting there.
Sure. Okay. I see.
But I'm actually working on a paper where we address that. People have addressed that in the past, but I think there is
Interesting.
from the entropy perspective, there's much more insight there that people haven't uncovered yet.
Cool.
Okay. All right. So
Awesome.
I'll be back in a few months, hopefully.
Yeah, I was gonna say.
All right.
Awesome.
Okay.
All right.
Thanks
Well,
everyone
if
for
no one
your
else has any other questions, I was gonna say thank you, Akhil, for presenting. And yeah,
happy
I
to do
think with
so.
that, we'll call it a day.
All right. Okay.